Good morning, everyone. It's almost 9:15, so I think we can start. Welcome. My name is Roberto Mandrioli, and of course, as everyone now knows, I will give you lessons on environmental and toxicological chemistry. I see that you are 13, I think. So I think maybe just like other years, someone from the first year is following my lessons, even though the course is at the second year, but this is just normal. And we will talk about it later on the options to take the exam anyway, okay? So, as you have seen, I start the lesson at 9:15, and this will happen every lesson day. And I also take a break at the end of each lesson hour. So at 10 and 11, about 10 or 15 minutes. Okay, so everyone will have the chance to rest a bit. I don't know, eat or drink something and so on. Okay, because 3 hours of environmental chemistry are a bit tough for everyone, for you, but also for me. I have to talk all the time, so I need some rest between hours. Okay. If you want to talk, please don't be shy and tell me anything you want to tell me. Please, I mean it really, please interrupt me at any time when there's something you don't understand, when you have some doubt, when you want some clarifications, and so on and so forth. Okay? I mean, of course, the lessons are the aim of giving you an overview of this quite wide topic. And of course, they are useful if you understand everything I'm saying, if you don't have any problem with it, and so on. So I repeat myself, but please stop me when there's something to ask. Okay. Okay. So just a moment so that I can start my presentation. Okay. I think this should do. Okay. Just a moment. Okay. Okay. Now, I think everyone should see the my slides, and if you don't see them, please say something. As you hopefully can see here at the right, I keep the chat. Okay, so if anyone wants to ask me something in the chat, please do so without any problem, because I will see it and I will stop and answer your question. Okay. maybe sometimes when I am speaking, I will not take a look at the chat, so please be patient and allow me a few minutes to see your message and hopefully to answer as soon as possible. Okay. Okay. So no one is saying anything. So I think you are seeing my slide. This is my personal info at the university. Of course, my email is name.surname@unibo.it. This is my office phone, but please note that I am doing smart work right now, and this is the reason all my lessons will be online. So it's quite difficult to find me at this phone number, so it is better usually to write down an email to me. Okay. And I am at the Department for Life Quality Studies, which is the department here in Rimini. I mean, when I'm not in smart work, but I live in Rimini, so I'm, let's say, at hand quite often, even if I'm not in my office. So here you can see two books that you can peruse for your interest in toxicology and environmental toxicology. However, please note that you don't need them. You don't need to study them for the exam. These books are only for, let's say, get in deep in some topic within toxicological chemistry, if you want, okay? Of course, no one needs to buy the books, and both of them are available at our Rimini University Library. Okay, so you can loan them if you want. Okay, of course, for free. Okay, so as you will see, the course is broken down into two main parts. The first part is an introduction, and this introduction will give you some basic concepts about chemistry, about biochemistry, and in general about toxicology and pharmacokinetics of toxic substances. This is, of course, an introduction meant to take everyone to the same page, the same level. So everything that comes after will be clear for everyone. So please be patient and let's say don't be angry if I will say a lot of things you already know. Let's take it as a repetition of useful concepts. Okay. So let's start with chemistry. Of course, the course is called environmental and toxicological chemistry. So the basis is chemistry, and of course toxicological chemistry. In fact, every toxic substance has properties, and those properties are basically due to their chemistry, to the way they interact with the chemical structures of the body, of the environment, and how the reactions are going between the toxic compound and the living and non-living organisms and environment. Okay, so everything that exists is a chemical substance, and every substance is composed of one or more of about 100 fundamental basic kinds of matter. And these 100 kinds of matter are called elements. Just like the name says, these are the elements on which everything is built. One element is composed of very small particles called atoms, and all atoms of the same element are exactly identical from a chemical point of view. They have the same chemical behavior. We will see in the following that not all atoms of a specific element are exactly identical. Let's say physically it's identical, but chemically they behave in the same way, or almost always in the same way. And each one of those 100 elements is individuated by an atomic number and by a chemical symbol. And those are always the same, okay? Every time I talk about carbon, the symbol is C, and its atomic number is 6. So if I say carbon, or if I say the element with atomic number 6, this is exactly the same thing, okay? Atomic number 6 or carbon is the same thing, just like potassium with K and 19, cadmium with CD and 48, okay? So the atomic number is the main characteristic of an element, and it's always the same for a specific element. Moreover, in addition to the atomic number, we will see right now in the following what the atomic number means. We have also an atomic mass. The atomic mass, usually when you see the atomic mass of an element, you'll see the mean atomic mass, because the atoms of a specific element can have small variations, small changes in their atomic mass. Usually most atoms of an element will have a specific mass, but at least some small percentage of those elements will have slightly different mass. So the mean mass is a, let's say, constant characteristic of an element, but it is just a mean, okay? It's an average. So every atom will have a characteristic mass, and within the same element, this mass can change a bit. The atoms, in turn, are constituted by 3 kinds of different subatomic particles. And those subatomic particles are the proton, the neutron, and the electron. The proton is here in the very, very small part of the atom. This is much bigger than, of course, this is much bigger than an atom. But the proportions here are not correct, let's say. The nucleus is much, much smaller than this electron cloud around. Okay, so most of the atom is void and is just, let's say, an electron cloud. Okay. Oh, sorry, I forgot a quite important thing. Would you want for me to record the lessons? Because of course I didn't start it. I didn't start the recording.
Yes, please.
Yes.
Okay. Okay. So as you have just seen, I tend to forget the recording. So please recall it to me every time. Okay. Every morning when we start the lesson, please say to me, start the recording, because I will forget for sure. Okay. Okay, so let's start the recording. Yeah. Okay, as I was saying, the nucleus is very small, and all around there's mostly void with a very, very small, much smaller than the proton, particle called the electron. One or more electrons. These are very, very small. So most of the atom is really void. The proton has an electric charge, and it is a positive, single positive electric charge. Together with the proton in the nucleus, we can have one or more neutrons. Neutrons have roughly the same mass as the proton, but they don't have any charge. As the name says, neutrons, they are neutral, okay, uncharged. Sorry. Okay, I want the chat, not my transcription. Proton and neutron have mostly the same mass, the same weight, okay, which is conventionally taken as the unit, but the neutron has charge 0. Both are in the nucleus. The nucleus is very, very small. So around the nucleus, we have this electron cloud. We don't want to start talking about the real nature of this cloud. Let's say that the electron is more or less orbiting around the nucleus, so it is not still. It travels at very, very fast speeds around the nucleus, and the electron has a mass, a very, very small mass. It's almost 0. Of course, it's not 0, but it is very, very small. It's about 10,000 times smaller than the proton and neutron mass, but its charge is -1. So the same charge as the proton, but the different sign. Okay. Usually in the nucleus, we will have mostly the same number of protons and of neutrons. So if, let's say, for example, carbon has atomic number 6, this number is the number of protons, okay? So here in the nucleus, carbon has 6 protons, and most of the carbon atoms will also have 6 neutrons, okay? So usually the number of protons and neutrons are the same. If we change the number of protons in the nucleus, the element will become different, okay? So if in the nucleus we have 6 protons, it is a carbon atom, whatever the number of neutrons. If in the nucleus we have 7 protons, the atom will be different. If we have 5 protons, the atom will be the element will be different, okay? If the number of protons changes, the element changes. If the number of neutrons changes, the element doesn't change, okay? Mostly the number of protons and neutrons is the same, but it can change, okay? So most carbon atoms will have 6 protons and 6 neutrons, but it can have also 6 protons and 5 or 4 neutrons, or 7 or 8 neutrons. Just for your information, when the atomic number rises, so for atomic numbers like 40 or 50, the number of neutrons becomes even larger. So the normal atom for high weight elements will have a lot more neutrons than protons. And at some time along the weight increase, the nucleus becomes unstable, and those are called radioactive elements, because the nucleus is unstable, and so it tends to lose some neutrons, some protons, in order to become lighter and more stable. Okay, this is due to the fact that protons, of course, have all the same charge. So when we have a lot of protons in the nucleus, they tend to repel each other, and the nucleus tends to, let's say, explode, to lose at least some protons in order to have less concentrated positive charge and to become more stable. And the high number of neutrons stabilizes the nucleus. So this is the reason why higher weight atoms tend to have a much larger number of neutrons in comparison to the protons. If the atom is neutral, and when we talk about atoms, the atom as such is electrically neutral, we need to have an equal number of electrons as the number of protons. So again, with carbon, it has 6 protons in the nucleus, so a neutral carbon atom will have 6 electrons around the nucleus. Okay? Okay. As we have said before, atoms can have the same number of protons, so they will be all the same kind of atom, let's say carbon, let's say potassium, but they can have different number of neutrons in the nucleus. Of course, different number of neutrons means different mass, because of course we have seen that neutrons have a considerable mass. So same atomic number, different atomic mass. Those are called isotopes. So those are the isotopes of the same element. So we usually in again always the same example, carbon. Carbon has 6 protons in the nucleus, and most carbon atoms will have also 6 neutrons. So since the weight of proton and neutron is conventionally 1, we will have total mass 12, okay? 6 protons, 6 neutrons, total mass 12, okay? But a few atoms of carbon are isotopes with different number of neutrons. So, for example, 6 protons and 7 neutrons. the total is, of course, 13. So we can call it carbon 13, okay? Or 8 neutrons. So the atomic mass is 14. So this is called carbon 14. Usually, the most important isotope, in this case, carbon 12, is not called carbon 12, but just carbon, okay? Only when one of the isotopes is much less abundant than the main one, we give the number, okay? Okay, so as I have said before, when the atomic mass becomes much large, so for masses quite large, more than 50 or 60, many elements or all elements of very high mass are radioactive. Their nuclei are unstable, and they give away charged particles. They give away radiation in order to become more stable. We know that the radioactivity can have a very bad effect on human and in general animal and also on vegetable health. Okay, so radioactivity interacts very intensely sometimes with the living cells, and it has the chance to disrupt how cells work. And of course, it also can cause problems in the environment because the environment is mainly constituted by living beings, okay? Be they trees or animals or something like that, okay? Okay, so in symbols, here we can see the atomic symbol, so C for carbon, K for potassium, CD for cadmium, and so on and so forth. And at the bottom left of the symbol, we can place the atomic number, and the upper left of the atomic symbol, we can write down the mass number. So here we can see the most simple element, which is hydrogen. Hydrogen, the most abundant form of hydrogen, is hydrogen 1. This means that it has, of course, atomic number 1, and it has just one proton in the nucleus and one electron when it's neutral. So we can write 1 for the atomic number in the bottom left and 1 for the atomic mass in the upper left corner. But two important isotopes of hydrogen exist. They are so important that they have an independent name, okay? Normally, for another element, we would say hydrogen 1, hydrogen 2, hydrogen 3, but for hydrogen, they are quite important, so they have an independent name. They are usually called deuterium and tritium. And that is something, it has something to do with Latin, deu, or Latin or Greek, deu means 2, and of course 3 means 3. And so deuterium will have, of course, the same atomic number, just like tritium has the same atomic number like hydrogen, because the atomic number doesn't change for the same element, but they are different isotopes, so the atomic mass changes, okay? So deuterium will have one proton and one neutron in the nucleus, so it is hydrogen 2, atomic mass 2, and tritium will have one proton and 2 neutrons in the nucleus, and of course the mass is 3. the number of protons doesn't change, and the number of electrons doesn't change, 1 and 1. The number of neutrons changes, and also the mass changes. So each individual atom has a mass which is mostly an entire number, okay? 1, 2, 3. It has not decimal places. It's not 1 point something or 2.1 or so on. Okay, 1, 2, and 3 mass, because atomic mass is conventional to 1. But since when we take any amount of hydrogen is a gas, so we take some volume of hydrogen gas, about, let's say, more than 99% of hydrogen gas is hydrogen 1, but a very small percentage of gas will be deuterium, so hydrogen 2, and this is about 1 in 6,000 atoms. So it is a very small percentage. And this is an isotope. Almost no tritium will be present, because tritium, as we have said before, is a radioactive isotope of hydrogen. Okay, so almost all hydrogen in naturally is hydrogen or deuterium. Those are stable isotopes. Okay, not all isotopes are radioactive. Hydrogen and deuterium are stable. So in some volume of hydrogen gas, we will find a lot of hydrogen, a very, very small amount of deuterium, and almost no tritium, because tritium is radioactive. It loses neutrons in order to become deuterium or hydrogen, okay? Okay. So those are the isotopes. We have seen before that in order to be neutral, the atom has to have an equal number of protons and electrons. But quite often, let's say, many atoms tend to lose or to acquire electrons. Okay? So, of course, since the electron has a negative charge, if a neutral atom loses 1 or more electrons, it will take a 1 or more positive charges. If an atom acquires 1 or more electrons, it will also take 1 or more negative charges. So the atoms having a higher or lower number of electrons, and so some electric charge, are called ions. So if the number of protons and electrons in the atom is different, we have an ion. For example, in this page, sodium, the neutral sodium atoms, has 11 protons and, of course, 11 electrons. So 11 positive and 11 negative charges. And we write it as Na without any symbol. However, it is quite easy, really mostly sodium loses 1 electron, to give the positive ion, which is called the cation, and it will be represented by this symbol Na+. In the same way, or let's say in a similar way, chlorine tends to take electrons, and so it tends to take a negative charge. So we can write the neutral chlorine atom as Cl, and the negative ion, which is called anion, as Cl-. in the upper right corner. So we have cations, positive ions, and anions, negative ions. Okay, all the 100 and let's say 118 elements known are usually arranged in a specific way in a table. Of course, like every table it has rows and columns, and this is called a periodic table. It is called periodic because the chemical properties of compounds change periodically along the rows, but we will see it in the following. The atoms are arranged in strict atomic number order. Okay, so we start from the upper left with 1 hydrogen, and then we go along the rows from the upper left to the lower right. So from 1, 2, 3, 4, 5, 6, and so on, until 118. Theoretically, the periodic table should be much wider than you usually see in images than this. Okay, why? Because here, between barium and lutetium, and between radium and lawrencium, there's a series of other elements. Here, the elements from 57 to 70 and from 89 to 102 should be here in between. So the complete table should be much wider than this, but in order to have a more compact look at the table, usually those are listed here below the rest of the table. But if we take those elements and put them in the right order here, the atomic number order is absolutely perfect. Okay, it's very strict, or a very strict order in the table. Okay. Okay, so here in this table, of course, images of the table, the periodic table, can change a bit according to the most important properties that someone wants to highlight in the table. But all tables, of course, contain some basic information, and this is the atomic symbol, the atomic number, and usually the element name, and mostly the average mass. As you can see, the average mass is different from the atomic mass because it is usually not an entire number. It has decimal places. Why? Because it is an average. Okay, if you take hydrogen, most of the hydrogen is 1, mass 1. Very few atoms have mass 2, and almost no atom has mass 3, but very few atoms exist. So if you take the average of all these atoms, it becomes not exactly 1, but in this case 1.01. Of course, more precise estimates of this average exist with 3 or 4 decimal places, but it is not interesting for us. Okay, the important thing is to have a clear concept. Okay, in this table also, this is a quite simple table. We just have the basic info like symbol, atomic number, name, and average mass, and we also have another number, which is electronegativity. Electronegativity is the characteristic of an element which is able to attract electrons. Okay, so if an electron tends to keep its electrons very near to itself and to take electrons from other elements, it is a high electronegativity atom, and it will have an high electronegativity number value. Of course, the reverse is right. So an element that tends to lose electrons will have very low electronegativity values, but we will see it in the following in a moment. Okay, so in the table, all elements are arranged in a way that, according to the increasing atomic number, they become grouped along the columns in different groups or families that have similar properties, similar chemical properties. Okay, so when we arrange the table according to the increasing atomic number, atoms will have periodically similar properties, similar chemical properties along the columns. And this is the reason it is called a periodic table. So these are called groups or families or even periods, okay, due to the fact that it is the meaning. So apart from hydrogen, which is an element by itself, let's say, here, this column, the first column, the first one here, lithium, sodium, potassium, rubidium, cesium, and francium, is called the alkali metals column or group, and so on. Then the second one is the alkaline earth metals, beryllium, magnesium, calcium, strontium, and so on. Then here we have the transition metals, and most elements that we know as metals are included in this in those periods. Okay, so for example, chromium, iron, cobalt, nickel, zinc, silver, gold, mercury. Okay, or everyone knows that those are metals, and they are included in the transition metals groups. But also the first and second groups are metals, alkali metals and alkaline earth metals. Then we have post-transition metals. Here you can see the color code, okay? It changes according to the group. Here are the post-transition metals. They are still metals, like, for example, lead or tin, but they tend to change their properties from the transition metals to something similar, let's say, start to become similar to non-metals. So we can see that the large majority of elements are metals. All of these elements in this part of the left part of the table are metals. Aluminium is just like hydrogen, is in between metals and non-metals, but it's mostly acknowledged as a metal when we talk about some let's say cans or the frame of a window. We think about aluminium as a metal, okay, and it mostly has metallic properties, but it has some begins to have some non-metallic properties. And here in the right part of the table we have non-metals, Here the color code is not really terribly exact, because not only these are non-metal, but also halogens are non-metal. But this is a specific group of non-metals, so it is a group by itself, but it is still non-metals. Okay, and the last class is noble gases here, and they are a class apart. They are not usually considered neither metal nor non-metals. And here we can see the color code again. Very important, very frequent elements are included in the non-metal group: carbon, nitrogen, oxygen, chlorine, bromine, and iodine. All of these are very frequent and very important in living beings, in cells, and so on. Also, phosphorus and sulfur. So those are the non-metals. These are non-metals of the halogen class, and these are rare gases. Of course, in between metals and non-metals, we have an intermediate class. Here it is in dark blue, and this is the metalloid, okay, metalloid class. Okay, so we have this zigzag line, and all elements in the two sides of the line are considered metalloids. So something in between metals and non-metals, apart from aluminium, like I said before, that is usually considered a metal, a transition metal, but it starts to be a metalloid. Okay. And apart, we have those elements that they don't really belong to any group. I mean, of course, the group go along the columns. So lanthanum and actinium, cerium and thorium have similar properties, but since we only have two atoms for each column here, it is not very useful, let's say, to consider all those groups. Okay, so it's only for the main part of the table. Okay, I see it's already 10 o'clock, so we take a break. And if you have any question, please ask in the chat, or open your microphone and ask right away. Please, I mean it. And of course, this is it's not the only options. The only option you have. If you in the following you think about the thing I said before, and you have any question, please ask. Okay. Okay. So I don't see any question. I don't hear anyone speaking. So let's stop here, and we will see each other in about 10 minutes. Okay? Okay. Now I go out from the lesson room, okay? But I will be back, of course, in 10 minutes. Bye. Okay, welcome back. Let's start the second hour. I don't see again any questions in the chat. I hope you are hearing me. Let's say well. Now, be alert, because I tend to forget something to start the recording, or the microphone off, or I forget to share my desktop, and so on. So if I forget something, please recall it to me. Okay, don't be afraid to say something. But the recording is going on, so I think this is good, and we can go on with our. Okay, thank you very much for confirming it. Okay, so we have seen that we can divide the periodic table into several groups that are mostly arranged according to the columns. Okay, I forget in the following. No problem. So the three big groups, or three big subdivisions, are metals, non-metals, and metalloids. Lanthanides and actinides are not exactly included in either group. They are mostly considered metals, and they are called rare earth metals. And as the name says, they are quite rare, so we will not discuss them in any detail. Okay. But they are here in between alkaline earth and transition metals, so they are called rare earth metals. So metals are usually solid at room temperature, but we have four exceptions: mercury, cesium, rubidium, and gallium. They are usually, when they are in their elemental form, okay, neutral atomic form, they are solid, shiny, they conduct electricity and heat, they have some physical characteristics just like ductility and malleability and so on, but we will not be very interested in those kind of properties. And as we have seen, most elements are metals. When we think about alkali and alkaline earth metals, we don't usually think in our everyday lives. I mean, we don't think about them as metals. For example, lithium or sodium. Sodium is not usually metallic. Why? It is a metal when it is in its elemental form, but it is almost never in its elemental form, because sodium is very eagerly losing electrons to become the sodium ion, which of course has different properties than the metal. So when we think of metals, we are mainly thinking about transition metals and in part post-transition metals, okay? But chemically, all these elements are metals. Non-metals are the elements included in this upper right part of the table. As you can see from the color code of the symbols, many of them are gases, those written in blue here. And just one is liquid, bromine, and the other are four, let's say, phosphorus, sulfur, selenium, and iodine are solids. So non-metals are of course non-metallic. So in their elemental form, if they are solid, the solid ones are brittle, not malleable, not ductile, and don't conduct neither heat nor electricity. Of course, this also applies to the gaseous one for the electricity and the heat conduction, but not the brittle, malleable part. And metalloids here in between have, of course, properties in between metals and non-metals. In particular, they tend to conduct electricity only in some peculiar conditions. For this reason, they are called semiconductor. The most important one, of course, is silicon. And as I think everyone knows, those elements are very important for the computer chip manufacturing industry. Not for chains, they are called semiconductor. It is called semiconductor industry because those are metalloids and they are semiconductors. Okay, they conduct electricity and heat only in specific conditions. Okay, so along the rows we have periods. So this is the first period, second period, third period, and so on and so forth. Along the period, the chemical properties of the elements are quite different. What is the meaning of period? The meaning is that in an atom, electrons are not around the nucleus casually, in a let's say random arrangement, but they are arranged in shells, okay, concentric, more or less concentric shells. And the outer shell, most external one, tends to host for the most important atoms, which are those one of the first two period, tends to have 8 electrons. So these levels, this period, are those corresponding to the filling of the outer shell of atoms. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the rare or noble gases have a full shell at the outer shell, and so they are very, very stable. This is the reason why they are called noble or rare gases, because just like noble people, they tend to stay apart from common people. This is, of course, a quite old people, let's say, conception, and they tend to stay apart from the other, let's say, common elements, okay, because they don't react with them. And they don't react because they have a full outer shell of electrons. So the periods corresponds to the progressive filling of the outer shells. Here we have outer shells made from 8 electrons. Here we have 2 outer shells, one made from 10 electrons here in between, and another one here and here from 8 electrons, and so on and so forth. Here we have another 14 electrons in the outer shell, and so on. But this is, let's say, not so important for us because right now let's say this is useful to understand why the elements are arranged in this way in periods. So when we fill one period, one outer shell, we start with the following one, okay, and so on. But the chemical properties are not similar for elements of the same period. The period is useful to arrange atoms in the table, but it's not useful to predict properties. What is useful is the arrangement in groups, okay, so the columns. And elements in the same column will have similar properties, and this is the reason we call them groups, and we say that this is the alkali metal group, because alkali metal all have similar properties. Lithium, sodium, potassium, rubidium all have the same properties. Not the same, of course, similar properties. Okay. Okay. Most substances, however, are not elements, are not elemental substances. Most compounds, just like the name says, are composed of different atoms, of, let's say, 2 or more different kinds of atoms. And in order to understand the shape and the properties of those compounds, we usually use structures. Structures are, let's say, representation of real world molecules. A molecule is simply an aggregation of different atoms, a stable aggregation of different atoms. And in order to understand molecule properties, we need some abstraction. We need to understand how the atoms are connected among them. And this allows us to predict some properties and to predict how they will react. And this is, of course, very important for chemists, but also for our topic, which is toxicology. Okay. We will see in the following that basically any interaction between molecules is a reaction. And, of course, also interaction which lead to toxicity are or involve one or more reactions. Okay, the most usual representation of molecules uses the so-called Lewis structures. Lewis structures show each atom as a symbol and the connection between atoms. These are called bonds. And bonds can be represented by one or more lines, usually straight lines, or by dots. This is less frequent, but we will see in the following. So the first step in drawing a Lewis structure is to understand how the atoms are bonded one to the other. And in general, when we have different atoms in a molecule, the central atom in the molecule is the least electronegative one. Okay, so if we have let's say a molecule which is made from, let's say, oxygen and sulfur, like sulfuric acid, since oxygen has an electronegativity of 3.5 and sulfur has an electronegativity of 2.5, sulfur usually will be in the middle, in the center of the molecule, and oxygen will be all around. Of course, several oxygen atoms will be all around sulfur. Okay, this is, of course, the most usual way. It's not an absolute. And hydrogen atoms and halogens, in particular halide atoms, are almost always peripheral. Why? Because the hydrogen atom has just one electron, and so it can only lose it. And losing it, let's say, by sharing it with another atom, it can form just one bond, okay? One bond is formed by the sharing or by taking or losing one electron. So hydrogen can only lose or take one electron, can only share one electron because it has just one electron. So it can just form one bond, and so it cannot be at the center of a molecule for obvious reasons. And also halogens, they tend to take one electron, and by taking one electron, they form one bond. So they tend also to be at the periphery of the molecule. They tend to form just one bond, so they can be at the external part, let's say, of a molecule. Okay, so this is just to have a mnemonic aid. Okay, so electronegativity goes from the left to the right, increases from the left to the right, and increases from the bottom to the top. So here, oxygen, fluorine, and chlorine are the elements with a higher electronegativity, 3.5, 4, 3.0, okay? Also nitrogen, 3.0, okay? Of course, noble gases, as you can see here, don't have an electronegativity number apart from krypton, or krypton, xenon, and radon, but this is usually quite high. And as we have said, they don't tend to react, so we will not see them in many reactions, so they are not very important. Their electronegativity is not very important. And here we have the lowest electronegativity atoms, here francium, cerium, and radon, 0.7, 0.9, 0.7, so barium, 0.9, so those are the low electronegativity elements, okay? Okay, so we have 8 main groups or families, 1, 2, 3, 4, 5, 6, 7, 8, okay? And this corresponds to the filling of the outer shell electrons. So all alkali metal will have just one electron in the outer shell. All alkaline earth metals will have just 2 electrons, in the outer shell. The outer electron shell is called the valence shell. And so on. Here we have 3 electrons, 4, 5, 6, 7, and 8 electrons in the outer shell. And here we have 1 or 2 electrons and low electronegativity. So those elements will tend to lose, respectively, 1 or 2 electrons. Here we have, for example, 6 or 7 electrons and high electronegativity. So since we have here 6 electrons, those elements will tend to take electrons because electronegativity is high, so the element tends to take electrons, and to take 2 electrons in order to complete the shell to 8. And here we have 7, so here we tend to take 1 electron to complete the level to 8. Okay, here we have already 8 electrons, so no electron given or taken. They already have the full electron, valence outer shell. Here, if we lose 1 or 2 electrons, we will have a completely empty valence level, and so the molecule, the atom is stable. Okay. So here we have resume of what I have just said. Okay. Okay. So alkali metals tend to lose 1 electron and take a +1 charge. Alkali earth metals tend to lose 2 electrons to form a +2 cation. And the class 3 elements tend to lose 3 electrons to form a +3 charge. And similarly, family 5 electrons have 5 valence electrons, so they tend to take or gain 3 electrons to form a -3 anion, group 6 -2 anion, 7 group 7 electrons gain 1 to form a -1 anion. Here in between we have also the 4 group here, carbon, silicium, and so on, and they have of course 4 electrons, and they don't tend neither to take, neither to give electrons. They tend to share electrons. So we will not find carbon 4+, neither carbon 4-, okay? Those are elements that don't tend to lose electrons, apart from those ones which are metals, and they tend to lose some electrons, 2 or 4, but this is not really important. So this is according to electronegativity, okay? So high number of valence electrons, high electronegativity gains electrons. Low number of electrons in the valence shell, low electronegativity tend to lose electrons. Okay, so most elements, even if they are single elements, like for example the hydrogen element or the nitrogen element, usually don't exist as individual single atoms. Most of the matter that exists as molecules. We have seen before that molecules are simply groups of atoms which are stably bonded together. So the force that keeps atoms together is called a bond, a chemical bond. So the hydrogen gas is not made up of single hydrogen atoms, but it is made up from hydrogen molecules. Hydrogen molecules are in turn made up of 2 identical hydrogen atoms. Okay, this is, let's say, a schematic representation of the molecule, and this is what you usually write down in a reaction, H2. Okay, these 2 in the bottom right part, in the bottom right corner of the atomic symbol, is the number of atoms of the same element in the molecule. And this is a Lewis representation. This is, let's say, the least frequent representation of 2 atoms. Here you can see the only electron, which is represented by a dot. And here you can see that hydrogen, two hydrogen atoms share the two electrons among them, one for each atom, so they both have two electrons in common, and this makes the two atoms stable, because the hydrogen is an exception. Usually molecules tend to have atoms with 8 shared or individual electrons, but hydrogen tends to have 2. So this is a diatomic molecule. It's a molecule made up from 2 atoms, and it has a single bond made from 2 electrons shared among the 2 atoms. So here we can see that we can, of course, join more molecules. There's not really a limit to the number of atoms that can be bonded in a molecule. We have very large molecules with thousands of atoms bonded together. This is another quite simple molecule, the water molecule. Here we have 2 hydrogens and 1 oxygen, and each hydrogen is bonded to the oxygen molecule. Here we can see a Lewis formula for water. Oxygen has 6 electrons in the valence level, in the valence shell, sorry. Just a moment. Here, oxygen is column 6, 1, 2, 3, 4, 5, 6. So 6 electrons, valence electrons, and you can think of them as those 1, 2, 3, 4, 5, 6. And each hydrogen atom has 1 electron. So when a bond is formed between oxygen and hydrogen, hydrogen shares 1 electron with oxygen, and oxygen shares 1 electron with hydrogen. So we will have 2 shared electrons between oxygen and hydrogen here and here. So hydrogen will share 2 electrons, or at least there are 2 shared electrons between oxygen and hydrogen, so the hydrogen is stable, it needs just 2, and here again. And oxygen in all shares 8 electrons, so 8 electrons is the full valence shell, so oxygen is stable. And as a consequence, the full molecule, water, H2O, is stable. Okay. So we can form at least 2 main kinds of bonds. In one kind of bond here, between oxygen and hydrogen, we have shared electrons. Okay, so each electron which is shared is, let's say, counted for both atoms involved in the bond. So this electron and these electrons are counted for hydrogen, which has 2, and for oxygen, which has 8 in total. Okay, and in this case, this is called a covalent bond. Covalent bonds can have 2 kinds, purely covalent and polar covalent. Purely covalent are, let's say, not so frequent, not so important, because it's only purely covalent bonds are only between 2 identical atoms. Here, this is a purely covalent bond, because the two atoms are identical, are the same, and so the 2 shared electrons are here in between, let's say, with equal density. Okay, the electron doesn't tend to stay more close to this or to that atom, because the electronegativity is the same, and so neither atom tends to take or to attract more electrons its way than the other, okay? But here, again, from the periodic table, oxygen has a very high electronegativity, we have seen it before, and hydrogen has a lower electronegativity. So in this case, the two bonds are not completely or totally covalent or purely covalent, but they are polar covalent bonds. Since one of the two atoms is more electronegative than the other, so the electron will be attracted to the more electronegative atom. They will spend more time, or the electron cloud will be more dense around the more electronegative atom. So the two shared electrons between hydrogen and oxygen will be more attracted to oxygen, and so they will be more closer to oxygen than to hydrogen. And this is a polar covalent bond. And then, so this is between atoms with the same or very, very similar electronegativity. This polar covalent is between atoms with different but not extremely different electronegativity. When electronegativity is very, very, very different between the two atoms, we have an ionic bond. In this case, we don't have any sharing of electrons, but the more electronegative atom will gain the electron, okay, and will take the electron from the less electronegative atom. So you may understand from the, here you can see, you can understand that when we have this kind of electrons with high electronegativity, which react with this kind of elements with very low electronegativity, we will have ionic compounds. Also, with metal, usually we have ionic compounds when they react with non-metals. But when non-metals react among them, here we will have mostly covalent bonds, because electronegativity is relatively quite similar. Okay? So, for example, if sodium reacts with chlorine, chlorine has a very high electronegativity, it will attract and take the electron from sodium. So chlorine will become chloride and an ion, 1-, and sodium will become a cation, 1+, losing 1 electron. And at this point, since chlorine has taken an electron and it is negative, and sodium has lost an electron and it is positive, the two ions will attract each other, opposite charge, electrical charges, they will attract, and this is an ionic bond, an ionic molecule. So for purely or polar covalent bonds, we have a sharing of electrons, and usually it is written down as a line between two atoms. One line if there's just one bond, two shared electrons. Two lines if we have a double bond, 4 shared electrons, 2 couples of shared electrons, or even a triple bond if 6 electrons are shared, 3 couples of electrons. When we have an ionic bond, we don't write down any line, we don't highlight any bond, but we can write the single charges, okay? We can explicitly write down the charges, Na+, Cl-, or nothing, NaCl. Hmm? Okay? Okay. Okay, so when atoms and molecules react, we write down an equation, and in this way we have on the left part the reactant or reagents, and on the right part the products. In between we have an arrow which is read as yields or gives. And so in this case we have 2 hydrogen molecules, or 2H2, plus 1 oxygen molecule, or H2, yields 2 water molecules, 2H2O. When we write a reaction, a chemical reaction, it should be properly balanced. Okay, so on the left part and on the right part, on the reactant part and the product part, we should have the same number of atoms of the same kind. So if we have hydrogen atoms, we should have the same number of hydrogen atoms on the left and on the right. In this case, we have 4 hydrogen on the left, 4 hydrogens on the right, and 2 oxygen on the left, 2 oxygen on the right, because this 2 is referred to the whole molecule, so 2 hydrogen 2 and 2 oxygen, and so 2 oxygen and 4 hydrogens. And also the same number of charges, of electrical charges, on the left and on the right. Okay, in this case we have 0 on the left and 0 on the right, but in other cases we can have different number of charges, but they have to be the same on the left and on the right, on the left as on the right. A particular kind of reaction is the redox reaction. Redox, as the name implies, is a reduction and oxidation reaction. Please notice that no redox reaction and no oxidation reaction exist, okay? Because redox reactions are defined as reaction where one species gains electrons and another species loses electrons. So if one species has to gain 1 or more electrons, some other species has to give them, and vice versa. If one species loses electrons, it has to give them to some other species. Okay. Electrons cannot be alone, free in solution or anywhere. Okay, electrons must always be connected, included in an atom. Okay, so if one species loses some electrons, they cannot go free anywhere, but they have to be taken, to be gained by another species. So for this reason, we cannot have reduction, which is a gain of electrons, without also having oxidation, which is losing electrons. Okay? We can, I mean, theoretically, write down half reactions. This is an half reaction, and this is another half reaction, and those half reactions can be called oxidation half reaction and reduction half reaction, but they are not full reactions. Okay, so full reaction are always redox. We can write down half reactions, but these are not, let's say, real. They are just useful for calculating, but they cannot happen all alone. Okay, in this case, for example, iodide two iodide ions lose one electron each, so in total 2 electrons, to produce an iodine molecule, I2. So here in this half reaction we have explicit electrons written down, and here, which is a reduction half reaction, we have again explicit electrons. So half reactions have explicit electrons, and they cannot happen alone. In a full reaction, just like here you can see the two half reactions combined in a full reaction, we never have explicit electrons. So every time you see an electron in a, let's say, reaction, it is not a full reaction, but it is an half reaction, okay? If it is balanced and includes electrons, it is not a full reaction, okay? So the two half reactions always happen together to form a full reaction, like in this case. And in a full balanced redox reaction, the number of electrons lost by the oxidized compound, here it is the oxidation half reaction, so iodine, the element, oxidizes, and here is the reduction half reaction, so bromine, in this case, is reduced. The number of electrons lost by the oxidized compound must be exactly the same as the number gained by the reduced compound. Only in this case, if the number of electrons is equal, we can have a balanced redox reaction. Okay? Okay. Okay. Most reactions, also including most reactions that lead to toxic effects by some chemical on cells or on some larger organism, happen in solution. A few reactions can happen in gas phase, but most reactions happen in liquid phase, and in particular in solutions. Almost no reaction happens in pure solid phase. So when we talk about reaction, and toxicology necessarily involves a lot of reactions, when we talk about a reaction, we talk about mainly reactions in solution. A solution is simply a mixture between two compounds, and this mixture, has to be homogeneous in every part of it. Okay, so all parts of the solution must be homogeneous, meaning it has to have the same exact composition qualitatively and quantitatively in every point of the solution itself. Okay? So I can sample my solution in any part of it, and I will discover that it has the same composition anywhere I sample it. This is a solution. Normally, a solution, of course, is a mixture, so it will involve at least two different compounds. And the compound which is present in the largest amount is called the solvent. And the compounds, of course, the other compound, at least one compound, that is present in a lower amount is called the solute. And the largest part, most solutions, are formed by the interaction of a liquid solvent and a liquid which is not so frequent, but mostly solid solute. So any mixture which is completely homogeneous is a solution, but the most important and the largest number of solutions is made up by mixing a liquid solvent and a solid solute. Okay? And when we dissolve a solid solute in a liquid solvent, we obtain an homogeneous liquid. Okay? A solution is called a saturated solution when we have dissolved in it the maximum amount possible for that specific compound. It means that if I add any more of that compound will not dissolve anymore. So usually there's a limit to the amount of a specific compound that I can dissolve in a specific amount of a specific solvent. Probably the simplest example is dissolving table salt in water. No, table salt, you know, is made up from sodium and chloride, so it's called sodium chloride. And if I dissolve sodium chloride in water, I obtain a solution, but this solution has an amount limit. I can dissolve at most, let's say, I don't know, but it's just an example, 3 grams per liter, 3 grams of sodium chloride per liter of water. So if I dissolve exactly 3 grams per liter of sodium chloride in water, I obtain a saturated solution of sodium chloride in water. If I add more sodium chloride, it will not dissolve anymore, and I can see it as a precipitate, as a solid residue within my mixture. Okay, this is a saturated solution. Of course, if I dissolve less than that amount, in this case, let's say 3 grams per liter, I will have an unsaturated solution. When speaking in approximate terms, we can also speak about dilute and concentrate the solution. Let's say that I dissolve sodium chloride in water. Okay, so if the limit is 200 grams per liter, if I dissolve, let's say, 200 grams or 180 grams of sodium chloride, that solution will be concentrated. If I dilute a much lower amount, let's say 0.1 grams of sodium chloride in 1 liter, of course, that solution will be a dilute solution. But this is just an approximate measure, and we will see the more exact terms in the next part. So we can stop for the second hour because it's already 11. And if you have any question, please speak up or write something in the chat. No? Nothing? Yes, I know most of you already know all of this, okay? But let's say that in this way we will have exactly the same starting point for everyone. So be patient, even if you are bored by all these very simple explanations. Okay? Okay, so I don't see any question right now, so see you in 10 minutes. Okay? Bye-bye, see you later. I'm back. So, I see that Alessia Pasotto has asked a question about TOXOAir. Okay, so this is an online course which we have developed together with some colleagues, toxicologists from my colleagues from here, from Bologna University, but also with several colleagues from other parts of Europe. It was an European project. And it has a lot of different topics on many different classes of toxic compounds. However, it is, let's say, mostly centered on human toxicity. Okay. I think it is, let's say, a good project. It was made to make the study of toxicology a bit easier, more enjoyable, and hopefully clear. But let's say that it is not exactly the same as this course. Okay, so you will not need to take it, or at least you will not need to take it in full. I will just ask you to take at least one topic of this online course and to follow it in full, and just this topic in full, and to take the test at the end. And this is, let's say, a prerequisite to my exam. So, in order to be allowed to take the exam, this exam, environmental and toxicological chemistry, you will need to connect to the TOXOAir page and take just one of the topics there, and take the test. Then you will send me the completed test or some, let's say, screenshot that you had completed it. Okay. And of course, no matter what is the result, it's not a problem. And afterwards, I will allow you to take the exam. Okay, to take the environmental and toxicological chemistry exam. Okay. So it is, let's say, it is mostly optional. You can use it as you want, because it is freely accessible for everyone, not just you who attend this course, but for everyone all over the world. So it's completely optional, except you have to take one topic for this course. Okay. I hope I've been clear, and I hope I have answered your question. Okay, it's perfect.
And what about the exam, the actual exam?
Yes, of course. The first question has reminded me that I still have to talk about the exam. Now, the exam will be quite simple. This is an optional course, so of course we don't want to be too strict about it. It will be a written exam, and it will be a multiple choice test. Okay, it is 15 questions. Each question is worth 2 points. And so the total, of course, is 30. We know how it works. Multiple choice, absolutely only things that I show you and I speak about during the lessons. Okay, so if you follow the lessons, if you take and study the slides, the PowerPoint slides, you will be able to take the exam, no problem. okay? And of course, you will be able to take a good marks.
Okay, and the slides, we can just watch the recordings, or are you gonna submit them to Virtuale?
Yeah. Allora, now, if everything if I did everything well, let's say, you should already have on Virtuale all the slides of all the lessons, okay? However, they are copied from last year. So they are the, let's say, old slides. Of course, every year I adjust something, add some small detail or take out something else and so on. So right now you have all the slides, all the entire course on Virtuale. But it is last year's slides. When I finish one lesson, let's say right now at 12, I will reread my slides, make some small adjustment, and upload them on Virtuale. So you will have, let's say in the afternoon, the first lesson, which is the new one, and all the others that will be the old ones. Okay, so and so on and so forth. So as we progress in the course, I will upload the new slides, but lesson by lesson. Okay.
Okay, thank you.
Okay, so I do this because if you want, you can download all the slides, and maybe you can follow better the lessons and so on, having the slides before you, let's say, outside my presentation. Okay, but of course you will have all the new slides in your Virtuale at the end. Okay. Okay. So, another thing, usually I give you the chance to take the exam as soon as possible after I finish the lessons. So our lessons are scheduled to finish, I think, at the end of March, 24, 25 of March. So immediately after, at the beginning of April or something like that, I will start taking exams. I think we already have a session scheduled on Alma Esami. You can take a look and report back, but I think we have some exam session scheduled, let's say on the 4th or 5th of April. Yeah. I have considered everything. Don't worry. So you will have. This is not. This is a detail that I didn't think would interest you much, but it is the same. You will have not 15 but 16 questions. Okay, so 15 questions are 15. Let's say normal questions that I think everyone could answer correctly after having followed by the course and studied the matter. Okay. Then we have a 16th question, which is much more difficult than the others, and it is considered for the Lode and also for the marks. Let's say the odd marks, okay? Because of course, having 15 questions, we only have the even numbers, okay? If you answer correctly to, let's say, 14 questions, you should take 28, but never 29. If you answer correctly to the 16th question, you will have 29. and so on and so forth. And if you answer correctly everything, you will have 30, and the 16th, you have the loud. Okay? Let's hope that everyone will answer correctly all 16 questions, okay? But don't worry. Of course, let's say most of you will have a very, very good evaluation, very, very good marks at the end. I think something like from 27 on 26, 27 and up, okay? 99% of my students in this course have this kind of marks, so you shouldn't really worry about the exam. Just worry about, let's say, understanding and enjoying, if it is possible, the matter. I think if you have chosen it, you have some interest in it. So I think it's much more useful to concentrate on understanding and making good use of the information I give you. Okay, the exam in this case, this is a small exam. It's an optional exam. So I think in this case the marks are a bit, let's say, unimportant. Okay, because of course every one of you will have very, very high marks, so don't worry about it. Okay. So sorry. Okay. If there's no other question, no. Okay. So we can go on with our lesson, and we were speaking about solutions, dilute and concentrated solutions. But what is usually more important is the way in which we express concentrations. We have different ways of expressing concentrations. Some are more frequent or more usual than others. One of the most frequent way is percentage composition, and it is usually used when concentrations are relatively high. So for relatively concentrated solutions, we use percentage. For example, 5%, 3%, 90%, something like that. Okay? In reality, percentage should never be expressed like this, 5%.
Professor, you're not sharing the slides.
Okay, thank you. I warned you before that I would forget. Okay. Now you should see them.
Yes.
Thank you. Okay. So you should never express 5% acetic acid or 3% hydrogen peroxide without some specification in between. Because we have different kinds of percentage, and we should always know which kind of percentage is this. Okay, so we have three main ways of expressing percentage: weight on weight, or more accurately, mass on mass, which is usually expressed as W on W or M on M; weight or mass on volume, W on V, and volume on volume, V on V. When we speak about the most common kind of solution, we speak about a solid dissolved in a liquid. So it is most usual to use weight on volume, because we have a solid, so we can weight it quite easily, and we have a solid solute and a liquid solvent, so we can measure its volume quite easily. Okay, so mostly percentage in solutions is weight on volume or mass on volume, but we have other kinds of expressions. So we should always specify which kind of percentage we have. Of course, for example, if we add weight on volume, we will have grams on milliliters times 100, and this gives the percentage. So we measure the weight in grams and the volume in milliliters. This is the percentage. Grams and milliliter, of course, mostly correspond or are very similar. Of course, for water, they correspond. 1 gram of water is equal to 1 milliliter of water. So this is the reason we use grams and milliliter. But for many solids, 1 gram is, let's say, not equal, of course, but similar, close to 1 milliliter if it is in solution. And of course, when you use weight on weight, we should use grams for grams, but we can use, of course, any kind of mass or weight expression, as long as it is the same on the numerator and on the denominator. Okay, so grams on grams, kilograms on kilograms, milligrams on milligrams, and so on. And the same is true for volume on volume. Okay, here we can use milliliters on milliliters, liters on liters, and so on. But for weight on volume, we should always use grams on milliliters, or multiples of both. Okay, so instead of grams per milliliter, of course, we can use kilograms per liter or milligrams per microliter. Okay, but they should always correspond. Grams, milliliter. Chemists very frequently use another expression, which is molarity. Molarity is the number of moles of our solute per liter of solution. You may remember that moles have the weight of the formula weight of that molecule. So if we take potassium chloride and we sum up the atomic weight of potassium, atomic weight of chlorine, the sum is 74.55. So if we take exactly 74.55 grams of this compound, we take 1 mole. So 1 mole is the amount in grams of a substance equal to its formula weight, equal to its molar weight. Sometimes I call it molar weight, which is even clearer, I think, because molar weight means the weight of a mole, okay? So it is clear that if I think this weight, this is a mole, okay? So if you dissolve 1 mole in 1 liter of solution, you have an 1 molar solution, okay? So on and so forth. When we have to express very, very low concentrations, molarity is not very, let's say, it's not really useful. if you don't use micromolar and so on. And also percentage is not useful. It is useful if it is some percentage point, just like this, 5%. But this means 5 grams per 100 milliliters. So it is a large amount for toxicology. In toxicology, we usually deal with much lower concentrations. And so we have to use different units. And one of the most important units is ppm. ppm is the abbreviation of parts per million. ppm. So parts per million in theory should only be used in an exact way for homogeneous units. So parts per million means 1 part of solute per 1 million parts of solution. So 1 gram in 100 grams of solution. Okay? This is 1 ppm. Of course, this is a percentage. 1 gram per 100 grams of solution. ppm means 1 part, so 1 gram per 1 million grams. This is the meaning, of course, 1 million of solution. 1 million grams is 1 ton of solution. So if you dissolve 1 gram of sodium chloride in 1 ton of water, it means 1,000 liters of solution, you obtain 1 ppm sodium chloride. Of course, you can multiply or divide both parts by the same amount. So if ppm is defined, let's say, as 1 gram per 1 million gram, or 1 ton, you can divide grams and tons by 1,000. So you will obtain 1 milligram per 1 kilogram. Is it the same? Okay, the same ratio, so the same amount. So ppm is 1 gram of solute per million gram of solution. As you may imagine, 1 ppm is a very low amount, but many toxic substances are so toxic that we need also ppb and sometimes ppt units. ppb means part per billion, and of course is 1,000 times more diluted than ppm. So if ppm is 1 gram per million grams, 1 ppb is 1 gram per billion grams. It means that we dissolve 1 gram of solute in 1,000 tons of solution. You can imagine that it's usually they say that it is about 1 drop in an Olympic swimming pool, more or less. And PPT is 1,000 times more diluted. So it means 1 gram in 1 million tons of solution. But some toxicants are toxic even at a few ppb or even some tens of ppt concentrations. So this is really toxic. Okay, the most common solvent, especially for biological systems, is water. water is quite particular, quite peculiar in its behavior, and in particular its properties as a solvent are mainly due to the fact that it is a quite polar molecule, but with covalent bonds. Okay, so the oxygen-hydrogen bonds are covalent, but very polar covalent bonds. So the molecule has a very, let's say, a relatively strong negatively charged part and a relatively strongly positively charged part. Of course, the negatively charged part is the oxygen side and the positively charged is the hydrogen side. And this means that this molecule can interact quite strongly with ions, okay? And when, for example, we have an ionic compound like sodium chloride, it is composed by sodium with a positive charge and chloride with a negative charge. Water molecules will be able to separate the two ions, and several molecules of water will go around the chloride ions with their positive, partial positive charge all around a single chloride ion, and a lot of molecules of water molecules will go around, will dispose themselves around the sodium ion, and this will create a water shell around each atom, each ion, sorry, not each atom, each ion. And this is the mechanism of solvation. In order to create a solution from a solid compound in water, every ion, if the compound is ionic, of course, every ion has to be totally, let's say, you should have a lot of water molecules all around the molecule, the ion. And each ion, each solute ion, should be separated from another ion of the same molecule. And water is particularly good at solubilizing, solvating ionic compounds. It is also quite good at dissolving polar covalent compounds. So, for example, sucrose, is an organic covalent compound. It has no charges, but it's very easily dissolved in water, as we know. This is because it's a very polar compound, and so water is very good at dissolving it. Okay, so water is also able to form the so-called hydrogen bond. It means that if we have a covalent bond molecule, what happens? That the positive part of water interacts strongly with the positively charged part, with the negatively charged part of a molecule containing oxygen, nitrogen, or sulfur atoms, and vice versa. For example, many compounds containing oxygen, organic compounds containing oxygen, exist, and through the hydrogen in water, we can form a, let's say, a weak bond between the positive hydrogen and the negative oxygen in the molecule. In this way, we can more easily dissolve the molecule in water. But it is not really important to know this right now. Let's just take it as a concept that water is very good at dissolving ions and polar molecules, okay? Okay, another basic concept that we should have very clear is the existence of acidic and basic compound. Acidic compounds are compounds that can release hydrogen ions in water. So, if we dissolve hydrogen chloride in water, it will release one hydrogen ion in the solution. On the contrary, a substance that takes hydrogen ions or releases hydroxyl ions is called a base or an alkali. In this case, we have the example of ammonia. Ammonia, in this case, reacts with water, gaining an hydrogen ion to form ammonium and releasing an hydroxyl ion. Okay? So, releasing hydrogen ions, acids, releasing oxyhedral ions, bases or alkali. In particular, in many cases, we can see that the reaction between acids and bases is, let's say, the first thing that happens in solution before most other reactions. For example, if we take sulfuric acid, H2SO4, and put it in solution together with calcium hydroxide, CaOH2, we can see that, we can know that sulfuric acid can release 2 hydrogen ions, and calcium hydroxide can release 2 hydroxide ions. So, in solution, they will react, or if we want to be more precise, the hydrogen ions will react with the oxyhedral ions to produce water. So, calcium hydroxide will react with sulfuric acid to produce water and a salt, in this case, calcium sulfate. But the, let's say, the important part is the acid-base reaction, where an acid, H+, reacts with a base, OH- ion, to produce water. This is called a neutralization reaction. It is called a neutralization reaction because we start from an acid, a base, and we produce water, which is by definition neutral. Okay, it doesn't tend to produce neither H+, neither OH-, so it is neutral, given the definition of acids and bases, of course. We know just a small number of strong acids and strong bases. At least just a few strong acids and strong bases are common in chemistry. What is a strong acid? What is a strong base? A strong acid is an acid which in solution is completely dissociated in its components. So when we solubilize hydrochloric acid, all molecules of hydrochloric acid dissolve and produce an equal number, let's say, an equal concentration of hydrogen ions and chloride ions. If I dissolve 1 mole of hydrochloric acid, in solution, I will find exactly 1 mole of hydrogen ions and, of course, 1 mole of chloride ion. But what interests me is the hydrogen ion part, because it is an acid. Okay, so it is the acid H plus ion which is interesting for me in this case. So this is a strong acid. It completely dissociates in water, producing an equal amount. 1 mole of hydrochloric acid produces an equal amount of H plus. Okay. Calcium hydroxide is a strong base. In solution, it will dissociate, producing an equal amount of oxyhydryl ions. In this case, however, since we have 2 oxyhydryl ions per molecule of calcium hydroxide, it will produce double the moles of hydroxyl ions. Okay, but the amount of, let's say, of oxyhydryl ions contained in a mole of calcium is exactly 2 moles. So all hydroxyl ions in the molecule will dissociate in solution. This is strong acid. This is a strong base. And strong acid and strong base are not very common. We have just a few, as you can see here, about 6 or 7 most important acids. It would be good to learn them by heart, the name and the formula. It is useful, let's say. So perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3, sulfuric acid and H2SO4. And in the same way, strong bases, as you can see here, if you remember the groups in the periodic table, here are the first 3, lithium hydroxide, sodium hydroxide, and potassium hydroxide, are the hydroxide of alkali metals, sorry. And calcium hydroxide, strontium hydroxide, and barium hydroxide are the hydroxides of the alkali earth metals. So the first 2 groups produce strong bases. Okay. All other compounds which are not strong acid or strong bases, all other acids and bases are weak acids and bases. In this case, for example, ammonia is a weak base. Why? Because when we dissolve ammonia in water, not all ammonia will become ammonium, producing oxyhydryl ions, but just a small part. Let's say that if I dissolve in water 1 mole of ammonia, 0.1 moles of ammonia will become ammonium, producing 0.1 moles of hydroxyl ion. The rest of the ammonia will stay in solution as ammonia. Okay, so when we dissolve hydrochloric acid in water, it completely dissociates and produces an equal amount of hydrogen ion. A weak acid or a weak base only reacts very weakly with water, producing hydrogen or hydroxyl ions. Okay, this is the difference. Okay, in order to measure the amount of hydrogen ions and, as a consequence, the amount of oxyhydryl ions in an aqueous solution, we use a value which is called pH, where P is a function and is exactly the minus logarithm function. To be precise, it is minus base 10 logarithm, you see that log is written with a capital L. So a capital L means base 10 logarithm. So the P part is minus logarithm in base 10, and the H part, of course, is the concentration of hydrogen ion. You may remember that the square brackets mean concentration in chemistry, of course. So pH is the minus logarithm of the hydrogen ion concentration. Why do we use pH? Because the concentration of hydrogen ion can change in huge proportions. We can go, for example, from 10 molar, 1 molar in this case, 10 to the power of 0, so 1 molar, to 10 to the power of minus 14, and all in between, all values in between, of course. So it is very strange, let's say, and not so easy to use all these exponential expressions. So in order to make it easier to use all these wide, huge range of concentrations, we use the minus logarithm. And as you can see here, pH, or the minus logarithm, is very easily correlated to the exponential expression, because 10 to the power of minus 6 means pH 6, okay? So we just have to take the number at the exponent. Of course, the signs should be changed. So we have a main scale for pH in water that goes from 0 to 14. Of course, we could use pH also for higher concentrations of pH. We could, of course, nothing prohibits having 10 molar concentration of hydrogen ion or 100 molar concentration of hydrogen ions. But when concentrations are high, numbers are more easily handled. Okay, you can say 1 molar, 2 molar hydrogen ions, no problem. In this case, pH would be negative, -1, -1.5, and so on. So it would be not very useful. It is useful for very small concentration, from 1 going down to minus x. Okay? So for concentration under 1 molar, it is much, much easier to use pH, minus logarithm of the concentration of hydrogen ions. And water is neutral by definition, 7. All solution having a lower pH value, meaning higher concentrations of hydrogen ions, are acidic. All solution with a higher pH, meaning lower concentrations of hydrogen ions, are basic. Since water is neutral, it dissociates, producing exactly 1 to the power of minus 1 times 10 to the power of minus 6 moles of hydrogen ions per liter. So 10 to the powers of minus 7, pH 7. Of course, lower amounts of hydrogen ions means higher amounts of hydroxyl ions. And in fact, basic solutions have very high amount of hydroxyl ions, because bases produce hydroxyl ions in solution, and very high concentration of hydroxyl ions mean very low concentration of hydrogen ion, and vice versa, of course. Okay? Okay. For today, I think everything was very simple. I don't think there's anything that you didn't already know, but we have repeated it. It is always useful. And so, if there's any question.
Sorry, Professor, when you said that basic solutions have lower concentration of hydrogen ions, but higher concentration of what?
Hydroxyl ions.
Hydroxyl. Okay.
Yes. OH minus. Okay.
Okay, thank you.
Welcome. Here, okay, this is a base. It produces hydroxyl ions in solution. So in a basic solution, we will have a high concentration of hydroxyl ions. And the two concentrations, hydroxyl and hydrogen, are inversely proportional. Okay? So if H plus increases, OH minus decreases, and vice versa. And so, basic solution, high concentration of hydroxyl ions, low concentration of hydrogen ions, high pH. Acidic solution, high concentration of H+, low concentrations of OH-, low pH. Okay? Any other questions? No? Okay. Of course, you can ask me questions also after the lessons. You can write your question in the chat, okay? I will read the chat when I happen to go on Teams, or I will receive a message. So if you think about the lesson and something is not clear, or you want to ask me anything, also outside the lesson, let's say about the exam and so on and so forth, don't be shy and write in the chat, okay? Don't worry. So, thank you very much for your attention, and we will be back tomorrow morning at 9 o'clock. Bye-bye.
Thank you, bye.
Thank you, Professor.
Bye-bye.